Okay, are there any questions since last time? Okay, so I'm actually gonna skip quite a few slides here because I want to get into the next section. I don't want to dwell in this section and to get to things that are actually interesting. So last time we were talking about basic operations of covering arrays, where if you delete a column, then I can't need more rows than the one with more columns. So if I take 8 columns and I take one of them out, then the optimal number of rows for 8 columns must be at least as large as the one for 7. Then we saw 2 more that are a little bit more complicated, but it's basically we can remove a row if we have one fewer symbol, one fewer value. And for derivation, we can get a whole lot of rows removed, but we sacrifice one in the strength. So if we sacrifice, if we go from strength 4 to strength 3, we can eliminate a lot of rows in that way. So we talked about that last time. There's several improvements that you can do for strength 2, and one of the project ideas is, can we do better than just removing one row for strength 3 and up? For strength 2, we can remove 2 rows. But for strength 3 and up, we don't know if we can actually do better. So are there cases that we can actually do better? So that might be something that's worth exploring. There are some other operations here that I'm not going to go into. It may be useful for our projects. This is more of a reference than anything else. So augmentation is basically the opposite of fusion, where we removed a symbol. Here we're adding a symbol. So the basic idea is that you work one column at a time, and you add a number of rows with a new symbol in that one column only, with the rest of the entries copied from earlier rows. And there's this funny looking bound here that you get, but the thing that you should note, I guess I will talk about this a little. So the thing that you should notice here is v plus 1 over v. That's the same thing as saying 1 plus 1 over v. And so this is 1 plus 1 over v times the array number for TKV. And why is that? If the basic idea is that you pick a symbol that occurs really infrequently, so it occurs not very often. Well, we don't know the structure of the covering array, so what you do is you just note that the average number of times a symbol appears is 1 over v fraction of the time. So if there are 3 symbols, every symbol occurs on average a third of the time. But some may occur more often, some may occur less often, but we don't know that in general. So we know for sure then that a symbol must appear 1 over v of the time. So we just pick the one that occurs least frequently. We know that we can achieve 1 over v because we just pick one. The average number of times must be at most what the least frequently used symbol is. So pick the least frequently used symbol. It must be at most 1 over v of the time that it appears. So you just work with that one column at a time, and I have an example here. So the idea is that if you look at these 3 rows right here, the ones with 2's in them, what you do is you copy the other 3 entries, the other columns, and just change the 2's in the first column to a 3. And then what you do after that is you pick let's see, which ones did we pick? Let's see, so I think we picked that one. Okay, no, I'm not sure. But what you do is you pick a symbol that occurs least frequently in column 2, and then add rows changing that one symbol to the new one. So here we're changing, I think, the ones that have a 2 in them. So this row, this row and that row. So I'm looking at the 2's in column 2. I copy those rows down, and in column 2, where I have the bolded entries, I change those to a 3. And you repeat for the 3rd and the 4th columns. And by doing so, you'll have 4 values in each column because it's 0, 1, 2, 3, and you can show that it actually is a covering array at that point. Okay. What you can do for strength 2 is you can add all the symbols at once. So the basic idea is for strength 2, here is a strength 2 covering array on, I think, 9 rows with 3 symbols. Yeah, and then these 3 over here, these are a bunch of covering arrays with, let's see, 5 rows, 4, no, wrong order. Strength 2, 4 columns, and 2 symbols. And we know the construction for 2K2 is optimal. So 5 rows are what you get out of that. And what you do is you work with each of the symbols 0, 1, 2, the ones that you already have, and the other symbol in each of the copies here is just a new one that you're adding. So 3 is the new symbol we're trying to add. We just make a covering array with 0 and 3, another one with 1 and 3, another one with 2 and 3. And then you just vertically juxtapose them together. So the second one will appear on the bottom. The next one will appear after the second one, and then the last one will appear after the other one. So you just vertically put them all together. Any questions on that? Okay, and I won't talk about this one that much. The idea is we try to add a column. Instead of trying to delete a column, we're trying to add one. It's just that we may need additional rows because we have some interactions that we may not be possible to cover. So I think I asked you to do something on homework 2 related to this. I'm not sure. But basically, you're just trying to... Oh, no, not on homework 2. Never mind. The basic idea is that... I won't go into it. But the idea is that you work with the new column and t minus 2 other ones because you duplicated a column. So you take a column, you duplicate it, and then now if you have an interaction that works with exactly one of the 2 columns, the one you had in the duplicate, then that one is still covered because you copied the column. But if you have an interaction with both of them, then you need to cover those interactions. So the 2 columns here, the one in its duplicate, and t minus 2 other ones, then you need to work with a covering array of strength t minus 2, and that's why that appears. I won't go into the details of that. I have a project idea here that's actually really interesting that I was able to get some improvements by trying to optimize some of the parameters, and it might be interesting to explore this into with a little bit more detail. Any questions on any of the basic covering array operations type stuff? Yeah.
So with augmentation, would you only need to augment a covering array when you're adding an extra symbol?
Yeah. So augmentation is when you're trying to increase the number of symbols, yes.
Okay.
Yeah. Yeah, I have no idea why they called it that, but and then derivations when you're trying to have fewer symbols.
Okay.
So derivation is fewer. Actually, no. Fusion is fewer symbols. Fusion is fewer. Augmentations add one.
Okay.
Can you go through the augmentation one example again?
Yeah.
Compare the second example of the different.
The example or the idea?
The example.
Okay. So the basic idea is that we have a covering array right here, and what we're trying to do is we have 3 symbols and we're trying to get 4. We're trying to get a covering array with some number of rows, we don't know, strength 2, 4 columns, but now 4 symbols instead of 3. So what you do is, let's look at this first column. right here. So we pick any symbol that occurs the least number of times. Well, the 0s, 1s, and 2s all occur 3 times. So it doesn't really matter which one we pick. But let's just pick the 2. So we look at these 3 rows right here. And we're just going to copy them down, and nothing special. And then what you do is in the first column, so normally if we just copy them down, we'll have something like this. Right? We'll just copy them down. But then what I'm going to do is in the first column only, I'm going to change that 2 to a 3, to a new symbol, whatever I want to call it. So then that's how we get this second array here. Then what we do is, well, we have 4 values in the first column, but 3 in the other columns. So then what we do is we work with the second column, for example. We pick a symbol that occurs least frequently in that one, and then copy all those rows down, change the 2 or whatever to a 3. And then we work with the third column, then the fourth column, and then now we have a covering array on 4 symbols. So an interesting project idea, I think it's on the project idea doc, is to, well, if we choose a different order in which to process the columns, we might get better results. So it's not necessarily the case that you can pick the first column, second, third, and fourth, and that'll always be the best you can do with this method, because we're adding rows after each of the columns are processed. So the counts for the number of times something appears in the other columns is going to change. So maybe it may be best to just choose the columns in a random order rather than just the first, the second, the third, etc. So that might be interesting. Any other questions though? Oh, that actually reminds me. I made the announcement on Slack that there are paper slots open. So there are some dates that you can sign up for. So some people signed up, but there are plenty of spots still open. And the first paper presentation is not this Friday, but next Friday. So I'll release the paper on Friday, but I need to have 2 people assigned to that day. So make sure to follow the announcement and send me an email with what day you want, and then we'll try to schedule you in. Okay, any other questions? Yeah, go ahead.
How did you get the last rows of the third column?
Which one?
Like of the third one.
Uh-huh.
Like how did you get the last rows?
So remember, we're looking at the second column now, and we're picking 0, 1, or 2, whichever one occurs the least frequently number of times. So let's see. So 0 appears 4 times, 1 appears 4 times, 2 appears 4 times. So it doesn't matter. So you can pick 0, 1, or 2. It doesn't matter. They all occur exactly the same number of times. In this case, we happen to pick 2. So look in the second column where a 2 appears. So that's this row right here, this row, and that row. And what we do is we just copy those columns down. Yeah, I could have equally picked 0 or 1. It doesn't matter. In fact, I don't even have to pick the one that occurs least frequently, but it's just advantageous to do it that way because I want few rows. Other questions? Okay, so let's move on to more math. No, I'm kidding. Actually, I'm not, but it's actually kind of an interesting topic. So what did we first say about the lower bound on can TKV? What was the elementary lower bound that we showed? Yeah. No, that we actually showed. I guess we did show that. Yeah. So we have big omega log k. But even before that, what did we show? That I'll refresh your memory. It's at least v to the t. That's what we showed before. Yeah, so what does this really tell us? So this says, let's look at this first bound. This says that if you let the number of columns grow and grow and grow and grow, the shape of the curve is like a logarithm, right? But what was another stipulation that we had to say on the log k here? Well, do you see a v or a t in here? No. So in fact, the constant that's hidden inside there depends on v and t. And it would actually be an interesting project to determine, at least with some certainty, what the constant actually is. Because there's actually been quite a bit of work on, for specific v and t, what is the constant that appears alongside there. And another thing that might be interesting is, well, what if the real bound was, say, log k, like v to the t log k plus v to the t log k, or something. So the big O notation or big omega or whatever notation actually hides not only the constant, but the lower order terms too, that it may depend on. And in fact, when we get to higher index covering arrays later in these slides, there is a lower order term associated with that. So that might be an interesting project idea too. So let's get into it though. So we're going to use something called the probabilistic method. Anyone ever heard of what probabilistic method is? Cool. So no one's heard of this. So it sounds really scary, but it's really, really simple. So let me do an example. So suppose I tell you a list of numbers. Just any arbitrary number. Can you tell me anything about that list of numbers? I'm not going to explicitly say what the numbers are. Do you know anything about that list of numbers? No, you know nothing because I haven't told you any information about it. Now, let me tell you that the mean, the average, is 5. And that's the only information I'm going to give you. No matter how nicely you ask, I'm not going to tell you anything other than the mean. That's it. Is there anything that you can tell me about that list of numbers now? I'm not going to tell you how many there are. Nothing other than the average. Is there anything that you can tell? In fact, there is something. Yeah, go ahead.
Maybe there's some, you can maybe guarantee that there's some number that's either less than 5 or greater than 5.
Yeah. So if the average is 5, can you say with certainty that there's some number, at least 5, in the list? Yeah. What about a number that's at most 5? Yeah. Well, I can't tell you if it's strictly less than 5 or strictly more than 5. It could be that every number is 5 in the list. But you know with certainty that there's at least one number at least 5 and one number at most 5. That's pretty powerful, given the fact that I only told you the average. So let's see, there's at least one number less than or equal to 5 and one number, it could be the same number at least 5. And you may think, okay, well, that's pretty simple. That's not really something that can be really used here. So it turns out that we can use this really, really well and get an actual upper bound on the size of covering arrays, just from this fact alone, which is pretty amazing. So how does the probabilistic method work? So we haven't really talked about construction algorithms for covering arrays. That that you just feed in the parameters TKV and out pops a covering array of some size. We haven't talked about that. You could just write the exhaustive array like you did in homework 1, but the thing is that's not really competitive, as you saw on the third question. So this happens a lot in research. If you have no idea how to construct something, just try it randomly. No thought into it, just do everything completely randomly and just see what happens. So we're going to actually do that. So the probabilistic method, all it is just randomly making some structure and then trying to guarantee something about that structure. So let's see. So what we're going to do is we're going to make an array with some number of rows, n, and some number of columns, k, and each entry is chosen uniformly at random. So if we're making an array right here, so if we have n rows, k columns, and we look at one entry right here, this one is chosen uniformly at random from the set I have here is 0 through v minus 1, but it doesn't actually matter what the values are, of course. I'm just picking some set. We'll never actually use the values themselves. It's just that we're picking things uniformly at random. And it's important that we choose them uniformly at random, because when we talk about independence between two different rows, we need the independence to work in our favor. So it has to be uniformly at random. There is some work recently that talks about doing something similar to this, but with a different probability distribution. Like I may pick a certain symbol with slightly higher probability and some with slightly less probability. Here, everything is completely uniform. So I choose 0 with 1 over v probability, choose 1 with 1 over v probability, etc. Any questions on that? So there's no thought. I'm not trying to be clever about this. It's just completely random. Okay. So we have a certain number of interactions to cover. By cover, I mean appears in the array. So we need all interactions to appear in the array. Why is it k choose t times v to the t?
V to the t is more about for the covering array.
For a set of t columns, I must see v to the t things.
Interactions, yeah.
Right. But then how many column choices, how many choices of t different columns do I have?
Yeah,
K choose t. So for k choose t, different sets of columns, I have v to the t interactions for those columns to see. So the total for the entire array is k choose t times v to the t. Okay. So then, well, if I just make this array randomly, it may or may not be a covering array. So it may be possible that the entire array is just all zeros. There's no ones, there's no twos, there's nothing in there. It could be that it's a complete covering array. It is completely random. So we need to think about what is the probability that we have a covering array. So what's the probability that we actually cover the thing, make a covering array? So let's focus on a specific interaction. So a set of t columns with a set of t values. And then we just want to, so what we're going to actually determine is the probability that it is not covered. Because we'll actually show that that's really useful in a second. So if we want to figure out the probability that it isn't covered, then how does that relate to the probability that it is covered? Is not covered versus is covered. What is the relation between the two? Yes, one minus the other one. Yeah. So let's figure out the probability that it is covered in these T columns. In these T columns. Well, it's easier to think about a specific row. So let's focus on a particular row. So let's just say for the moment that I have T column. Notability. I love you, but I hate you at the same time. Okay, so T columns right here. So remember, each entry is chosen uniformly at random. So what's the probability that the T values in this interaction appear in the exact order for each of these T entries? So for example, if our interaction T's values, let's just say, are 0, 1, 2, 0, 1, etc. We don't know exactly. What is the probability that we get exactly 0 in the first position, 1 in the second position, 2 in the third position, etc., all the way through? Well, if there are V values in each position, what is the probability that I get 0 in the first position? 1 over V, right. What's the probability of getting the 1 in the second position? 1 over V, because every entry is chosen uniformly at random. Well, then the probability of getting all T correct, all answers correct here, is 1 over V to the T. So that's where this number comes, this quantity comes into play. Because we need all T to appear exactly in the right order. So, and each one occurs with 1 over V probability of the time, and they're all independent. So the probability that it is covered in this particular row is 1 over V to the T. So the probability that it is not covered in this particular row is 1 minus that guy. So with a very, very high probability, I'm not going to cover this interaction in this row. Well, since all rows are independent, the probability that I just don't cover it at all is the probability I don't get it in the first row times the probability I don't get it in the second row times the probability I don't get it in the third row, etc., all the way down. Because all rows are independent from each other. So the probability that no row covers this interaction is the probability of a specific row raised to the power the number of rows that we got, which is n in this case. So then I do something interesting. I calculate the expected number of interactions left uncovered. Well, it's the number of interactions that we have, k choose t times v to the t, times the probability that it is not covered. And that gives us the expected number that is not covered. Why do you think I want to calculate this? To check if it's a covering array. Well, I'm going to ask a question that may seem really, really simple, but it's actually very powerful and goes back to the list of numbers question I was talking about earlier. Suppose we have a covering array. Could the number of interactions that are left uncovered be something other than an integer? Can it be like half an interaction uncovered? Or does it have to be an integer? It has to be an integer. Because it either is covered or it isn't. So that means that this expected number must be an integer. The actual number of uncovered interactions must be an integer. The expectation might be different. The average might be something other than an integer. But the actual number must be an integer. So how does that help us? So what if I told you, it goes back to the matrix theme, what if I told you that we have our expectation right here. So here's our expected number of interactions, and I told you that it is strictly less than 1. Not equal to 1, it is strictly less than 1. What does that tell you? That means the expectation is less than 1, but remember the list of numbers example. Suppose that the average is 0.8, and the list of numbers contain all integers, no fractions, but the average is 0.8. What can you tell me? No, the list of numbers.
There must be 0.
There must be a 0 in that list somewhere. Could there be numbers that are not 0 too? Yeah, it could be, because it's just an average. But there must be some number in that list that's 0. What does this tell us? This tells us if this is true, then that means that the average is strictly less than 1, which means that there must exist covering arrays with no uncovered interactions, because the number of interactions left uncovered must be an integer. So this is actually quite striking, that as long as we assume this, then we can guarantee that some covering array exists on these parameters with n rows. So we'll note here, the n is in the exponent, right? So the n's is upstairs. What we would want is n is less than or equal to something. So if I say that n is less than or equal to something, then the smallest number of rows possible must be at most the thing on the right-hand side, whatever that is. So I'm not going to actually go through all the details here, but notice something here. So if n is in the upstairs, how do I get it downstairs? Taking the log. So it turns out what you'll have is the log of this stuff and then dividing by other stuff. So I'm going to leave out all the details here because it's not really that interesting. But basically what you will have, yeah, so we talked about that first line. Yeah, so what you'll have is something where n is approximately the log of k choose t times v to the t divided by the log of other things, which I won't get into. But what I will tell you is that the k only lives up here. So the k is only in the upstairs, it's not in the denominator of the fraction. So how can we simplify this? So if we have a log of something times something else, how does that simplify? Yeah, you just add them. So let's see. So I'm going to move this down here. What are we doing on time? Okay. Paste. So as was pointed out, let's simplify this. I'm going to remove the downstairs because it's just some constant involving v and t, which we're going to ignore anyway. So this is the same thing as saying log of k choose t plus log of v to the t. How does the log v to the t simplify? Yeah, t log v. So that's no problem. How can I simplify the log k choose t? It turns out that it's quite, you could get a bound on it, but we're going to do something simple. So note that k choose t is always at most k to the t. It's a rather crude bound, but it's pretty simple. and it's sufficient for what we want to do here. So this thing on the right-hand side is at most log of k to the t, because the logarithm is a monotonically increasing function. So we can do that. Well, then we can just do the same trick that we did before, which is t log k plus t log v. And then divided by something else, but we don't care about that. In practice, we do care about it, but just for asymptotic purposes, we don't really care. So this bound actually is dependent on v and t, right? Because it has a t log k and then a t log v in there, and the denominator involves v and t. But what if v and t were just a fixed number? They're just fixed and they don't grow. What does this tell us? Well, the t log v on the right-hand side, if v and t are fixed, is that going to ever change? No. But the thing that does change is t log k, right? Is t, which is a constant number, times log k, but k is growing. So this tells us that n is at most some number times log k. So this tells us that I have no room. So this tells us that n is big O log k. Maybe I should redo that. Because I have the less than or equal to sign here. And another thing that you should notice is just because the expectation is less than 1, even if the expectation was larger than 1, there still could be covering arrays of the same parameters. This just guarantees it for us. And in fact, some recent work of mine actually looks at if we have the expectation larger than 1, what is the probability that we still get a covering array at the end? So that might be an interesting project idea too. But why can I claim theta log k here? If I just said O of log k, why do I say theta here? So big O log k, that's the upper bound on the size. Where's the lower bound? Where did we get that from? Yeah, we said it earlier, because every pair of columns has to be different. And when we talked about that before, we got a big omega log k. So big O log k gets us the upper bound, big omega log k gets us the lower bound. And since it's both log k, we get theta log k. So it is a constant times log k. Any questions on that? So one really annoying thing about this is, does this tell you how to make a covering array of logarithmic size? Does it tell you? No, it just tells you that it exists. So you may see in the literature that this is what is called a non-constructive bound. Or that this method is non-constructive or something like that. So it doesn't tell you how to make the thing, it just tells you it exists. So at some point in the semester, I don't know when, but we will talk about a method that meets this bound and is an algorithm. So it actually does produce the covering array of logarithmic size, which is pretty nice. Okay, how are we doing on time? Any questions about the probabilistic method? So it's a rather simple argument of just saying, just make the array at random, just look at the probability that it is a covering array, and then when the expectation of the number of uncovered interactions is less than 1, because it must be an integer, there must exist a covering array. So what you could do in principle is just make every possible array on those n rows, you will find a covering array at some point. But it's just, that takes a long time. Okay, so something that I've been working on recently, and so this isn't actually published, so I can't actually, it is published in my dissertation, but it's not published in, anywhere else. So how many of you have not looked at homework 2 yet? What do you think I advise you to do? Look at homework 2. Okay. So I reintroduced the notation here. So you may think, okay, well, for a covering array, every interaction appears at least once. But you may want to, for purposes of redundancy, have a covering array where every interaction appears at least a certain number of times, say 5 times. Then you may want to figure out, well, if I want to incorporate redundancy in some way, how many rows do I need in order to do that? Well, what you could do is, well, we just said that covering arrays where everything appears once, at least, has growth log k, is theta log k. So what you could do is just say the optimal bound for when I have a redundancy of lambda, where everything appears lambda or more times, is just, well, take the array where everything appears once, and then just juxtapose it lambda times. Don't do anything smart, just juxtapose it lambda times, and that'll definitely give you a covering array with redundancy lambda. Well, if each one of those was log k, well, if I do that lambda times, it's just lambda times log k. So that's why I have this here. But the problem is I can't claim that this is theta log k, theta of lambda times log k, because we don't have a matching lower bound. Whereas before, we did have a matching lower bound of log k. So we can just sandwich them and just say, oh, it's just something times log k. And it turns out we can do significantly better than this. So if we do exactly the same argument, except for everything appears at least lambda times, we can do exactly the same type of argument as before. So this looks like a very complicated equation, but let me run it down for you. So here we have the number of interactions like before. And this really funky equation over here, this is the probability of being covered less than or equal to lambda minus 1 times. So the notion of coverage here is changing from saying it doesn't appear to it appears at most lambda minus 1 times. So where does this come up? So how many of you have done probability in 290 of some sort? How many of you have ever seen this type of equation before? So here's the basic idea of how you can digest it. So we want to look at the probability of being covered exactly 0 times, 1 time, 2 times, 3 times, up to lambda minus 1 times. So that's where the I equals 0 to lambda minus 1 comes into play. Well, suppose that it is covered exactly I times. Well, it could appear in any set of I different rows. It could appear in any one of the of I rows. So that's where the n choose I comes into play. It appears in I different rows. Well, what's the probability that that occurs in those exact I rows? Well, the probability of coverage in those I rows times the probability of no coverage in the other rows. So this P right here, or P right here, is the probability that this interaction's covered in this row. Well, if it's covered exactly I times, then the probability of those particular I rows covering it is P times P times P times P I times. But it also must be not covered in all of the other rows, and there are n minus I of those. So the probability of no coverage is 1 minus P, and there are n minus I other rows. And then, well, any number of times between 0 and lambda minus 1 could possibly occur. So we just sum them all up. It's the same thing as saying, if I make a bunch of coin flips with some probability P, what's the probability I have fewer than, what's the probability I have fewer than lambda heads? It's something similar to that. It's the binomial distribution here. So you'll see this all the time if you look up binomial distribution of n choose I times p to the I times 1 minus p to the n minus I. It's the probability of lambda minus 1 or fewer successes in n trials. It's the same thing here. So I won't go into these bounds that I've obtained too much, but it turns out that this is actually really hard to analyze. Whereas before, we had 1 minus the probability to the n, where it was just a simple n upstairs, and then we just took a simple log to fix everything. What I encourage you to do, and if you can solve it, you should talk to me, is try this equation here with lambda equal to 2. So it'll be k choose t times v to the t times something plus something else. It's really, really difficult to extract the n out of the equation. Whereas before, there was only one instance of n. Yeah, so there's only one instance of n, so we could just take a simple log to fix everything. Here, you can't. So one technique that I thought, which seems kind of stupid, is, well, I don't know what this sum is, but what I could do is I can just replace each of the terms with the largest possible value that it could ever obtain. So for the n choose I thing, n choose 0 is 1, n choose 1 is n choose 2 is bigger, n choose 3 is bigger, n choose 4 is bigger. So it keeps going up. So what I could do is I just choose n choose lambda minus 1, the highest value it ever obtains. Well, p to the I, that's maxed when I is equal to 0. So I just put 1 here. And then for the other one, 1 minus p to some power, well, the smallest power possible is the highest value it could ever obtain. So when I is maximum, which is lambda minus 1, then that's the best we can do. So why upper bound? Because if this equation is less than 1, then the original one must be less than 1, which is exactly what we want. So I think that's enough for today, so I'll see you on Wednesday.